Okay, welcome back. In the last video, I introduced Gaussian elimination or Gauss's method as a way to modify a linear system. And I've described how you can read off the resulting echelon form, whether a linear system is uniquely solvable or whether there's no solution or whether the system has infinitely many solutions. So we are now particularly looking at the case that we have infinitely many solutions and in ways of describing this set of solutions. So here's an example of a linear system. If we do the row operations that I've introduced last time, we arrive at this system which is in echelon form, and now we would like to describe the set of solutions. And what you notice about this system is that there's no equation where the variable z leads. So x leads the first row and y leads the second row. So here we have this down and over shape. But then here z appears only with coefficient 0, so z is not leading any row. But then it's convenient to pick this variable, which will be called free, z in this case, as a parameter of the solution set. And let me show you this example, what I mean by parameter here. So we are going to express y in terms of z. So we are really taking the second equation in the system here, solve it for y, and then express y in terms of z. And once we have found an expression of y in terms of z, we can take the first equation to express x also in terms of z. You might think, well, we probably have to express x also in terms of y, but no, because y itself can also be expressed in terms of z. So if we plug in our expression for y in this first equation, then we can solve for x and express it also in terms of z only. So the result here is that we have expressed y in terms of z and x in terms of z. And then in this table, for example, we could list a few solutions. So in the top row, we could pick a few values for z as indicated here. And each value for z using these two formulas for y and x gives us a solution triple. So we could note in particular that x and z add up to 3 as suggested in this equation. So we could tell immediately that 1, 6, 3 cannot be a solution because 1 and 3 do not add up to 3. That's up to 4. Okay, so here's the definition. So the variables that are not leading in a linear system in echelon form are called free. And then the free variables are a convenient parameter to describe the solution of a linear system. Let me just show you another example. So the system is already in echelon form. You notice that x and y are leading these two equations respectively. So we will choose z and w to parameterize the system, and following the same procedure as just outlined, we arrive at an expression of y in terms of z and w, and we arrive also at an expression for x in terms of z and w. Okay, so this gives us a relatively succinct way of describing the set of solutions. Here's another example. We notice that x and z are leading, so y and w are free, right? So we are going to choose y and w to parameterize the solution. And using exactly the same procedure, we arrive at this. So here all four variables are expressed in terms of y and w. Here it's perhaps slightly different because z depends only on w, and x then depends on y and w. So I mentioned the term parameter. Maybe other people would prefer a kind of more, well, you might call it hygienic approach, where we distinguish between the variables and the parameters. So we might instead call the parameters differently. So maybe we call them A and B. So then we would say, well, on the right hand side, we would just write A and B. So here B and here also B. So now we have expressed x, y, z, and w in terms of A and B, and we would say, well, pick for A and B an arbitrary real number, and then these expressions here, these four expressions, give you a solution for x, y, z, and w, so a solution for the original system. So here we would have distinguished between the parameters and the variables, but never mind. So I think we don't have to spend so much fantasy and come up with other names for the parameters. We might as well just take the variables themselves. Okay, so here is yet another example. Again, of course, we use Gauss's method to put the system in echelon form. And now here it says the leading variables are x, z, and w. So here we go. We'll parameterize with the free variable y. Well, it so happens that if we do this back substitution process, w doesn't really depend on y, and neither does z. And y, well, in a sense, it depends on itself, if you will. And then x depends on y. Okay, so it's a little bit different than the previous examples, but nothing new conceptually. Let me introduce now something else. So we will spend a lot of time in this course talking about matrices and vectors. Particular matrices perhaps are the most basic and most central concept of linear algebra, really. So we might almost call linear algebra something like the science of matrices or something like that. But for the moment, we are just looking at a matrix as some kind of container for numbers. So we might say a rectangular array of numbers with m rows and n columns. Okay, so this is an m by n matrix with m rows and n columns. So here we have m rows and here we have n columns. The numbers are organized in some grid-like way. By the way, I will often probably accidentally say m times n matrix, so I might do that. I don't know yet. That's not quite right. I should say really m by n. I might say times, either because I translate from German or because the LaTeX command to produce this symbol is written times. But I'm sure you will learn LaTeX later on. Never mind for the moment. Anyway, it's called n by n matrix. And the numbers in the matrix are called entries. I might also sometimes say components, so I'm not going to distinguish between entries and components. So here's an example. It's a 2 by 3 matrix of numbers, 2 rows and 3 columns. And the entry in row 2 and column 1, so that would be this one, this 4, is 4. And in this course, so this comes from the textbook, of course, we are going to use small letters for entries of a matrix. So we use capital letters for denoting a matrix. That's standard everywhere, to use capital letters for matrices. It's not so standard to use small letters for entries, but it is a useful convention, but it holds only in this course for now, so this is not something that would be generally observed. Then a column vector, or often just called a vector because column vectors are traditionally more prominent than or widespread than row vectors. So we call a column vector often just a vector, and that's a matrix with a single column. And then a matrix with a single row is called a row vector, and the entries of a vector are sometimes called components, or again, I might just say entries. Column or a row vector whose components are all zeros is a zero vector. Okay, so for example here, it's a two-dimensional zero vector. And we denote vectors with an over arrow. Okay, so here you see it if you look closely. So it would look like this. Some authors use boldface for vectors, but if you write things by hand, which you might well do when you are a student of this course, then it's easier actually to write an over arrow over the letter. So that's hopefully convenient. Okay, so this is a row vector and has 3 components, and there's a 2-component zero vector, the same one that I've written before. Yeah, which could be called just 0 with an over arrow. So that's a zero vector. And then we have operations on vectors, and in fact we have similar operations on matrices. So the vector sum of 2 vectors is just the component-wise or entry-wise sum. It's sort of the natural way to define the sum of two vectors. Notice that it only makes sense if the 2 vectors have the same number of components, here n. Otherwise, it's not meaningful to have a sum. And then we have scalar multiplication. So that's given a number. In this course, would be usually a real number, r, and a vector v. And then we can define a scalar multiplication, which we just write as a normal multiplication with a dot. And it's defined in this way. So each component of the vector is multiplied or scaled with a scalar. By the way, we will not be overly concerned with notation here. So instead of r times v, we might also write just rv in the same way as if you instead a times b for some numbers, you might often just write ab. Some people don't like this, but we won't be worried, so we would also write vr, so the scalar after the vector. This is commonly also used, although some people don't like it, but to keep things simple and in fact intuitive, we will allow such notations. So here's an example using both scalar multiplication and vector sum, really. Right, so 3 times 1 is 3 minus 2 times 0 is 0, and then 3 minus 0 is 3. Similarly for the bottom component. So this would also be called a linear combination of vectors. In the previous video, I've defined linear combinations of variables, but it's natural to extend this notion to vectors. All right, so we might then use matrices to denote linear systems, perhaps to get rid of repeating these variables over and over, especially in a sense already the column indicates what the variable is. So it seems a little bit of an overhead to repeat this variable again and again. So we might just omit the variable. Of course, sometimes we would still refer to the variables by their names. So in this resulting notation, the variables don't appear at all. Perhaps if we want to make clear what names are associated with these columns, we might write the variables on top of these columns. In any case, I hope you see how this system and this augmented matrix are associated in a very natural way. So the matrix, the augmented matrix, just contains the coefficients. And then we can perform these row operations from Gauss's method in the same way that you expect. So we are again we're interested in this triangular form or step form, and we can do this just based on these augmented matrices. We can also do what I just described. So we would choose the last variable called z as a parameter, and then we might express x and y in terms of z. So that's done here. So we have described x and y in terms of z. And now a nice thing about vector notation is that it also gives us an organized way to denote the solution set. So the solutions could be written like this. Notice again, perhaps we might as well call the parameter differently, maybe a. Why not? We would not rename this. So here we should really have the variables, because the idea is here we really indicate the variables, perhaps the order of the variables. We would keep that set, but we might use a different letter for the parameter or not. So either is fine. Okay, so we're using column vectors, so this gives us also a nice way of describing a few concrete solutions. Here's another example. So we start with the system. We put it in the augmented matrix notation as just discussed. We use Gaussian elimination to put it in echelon form, and then arrive at a description of a solution set in vector notation. So here we have two parameters, z and w. Why? Because the last two variables, z and w, are free implicitly here, so they are not leading any row of this augmented matrix. X and y are leading, and z and w are free, so we would naturally use z and w as parameters of this solution set. That's it for now.